So welcome to the second meeting of our seminar here in Brno for Masaryk University. This is the second talk, even though this is the first one that goes live. And today we have again Christian Espíndola, who's gonna talk about Topos-theoretic completeness theorems. And now I leave the stage to Christian, who will introduce again the talk and then start giving it. See you later.
Okay, so here it is. All right, so this is intended to be a follow-up on the previous talk on the topos-theoretic proof of Sheila's eventual categoricity conjecture. But of course, since we gave the full outline of the proof in the first talk, we mentioned the key results that we needed to use, which were a couple of completeness theorems of a topos-theoretic nature. So those are the ones that I will talk about now by the end, but the idea of this second talk is to delve into the details of the first one. So to understand, especially because of the questions that have arisen in the audience and the feedback, I wanted to give an overview of what's behind this usage of topos theory to understand these accessible categories. The talk will be really a different from the first one, in the sense that all those details will be explained now. Maybe some of you know them already, but I wanted to set up all the background field so that, I mean, if you want this could serve as a sort of prerequisites for the first talk, and then if you go back to the first talk and take a look at it, you will hopefully understand it much better. Okay, so the first thing that I have to do is to talk about the logic of accessible categories, which is the logic that I've been using throughout the proof of Sheila's conjecture, because the AC is in particular an accessible category, and I have then it is axiomatizable by a certain type of logic. So let me define what it is. So first, a kappa coherent formula, which is also called positive existential in the book of Irgi and Adamek. In this case, is a formula of the form you have here, a disjunction of at most kappa elements, an existential quantification over a tuple of variables. Here, when I write the boldface X, it means that it's a tuple of variables, not necessarily finite. It could be infinitely many variables, but always less than kappa. And then a conjunction of indexed by an ordinal less than kappa, and the phi ij's are atomic formulas. And so they are either equality between terms or relation symbols applied to terms. And of course, the arities of these can be of any size less than kappa. So notice that there is an asymmetry here. I will talk about it later, because I do allow conjunctions of kappa different term formulas, but the variables over which I quantify and the conjunctions are always over strictly less than kappa. So so keep that in mind. So in a sense, these formulas belong to L kappa plus kappa. And then we have the notion of a kappa coherent sequent, which is called basic in the book of Irgi and Adamek, which is an expression of the following form. You have phi and psi on each side of the turnstile, and you have in the middle a tuple of variables, not necessarily finite, which contains all the free variables of phi and psi, but could be even bigger than that. The intended meaning of that sequence style expression is the sentence that for all x, for all tuples of variables x, phi implies psi. So this is a sentence. However, in the last talk, I was very careful to distinguish between a sequent and a sentence, because the thing is that to be able to talk about the sentence, you need additional symbols that you don't have available in the positive existential formulas. You need an implication here, and you need a universal quantification. Instead, a sequent formally only requires the positive existential formulas phi and psi, and this will be useful when we take a look at the categorical interpretation, because it will be possible to interpret sequence in much more general categories and toposes than interpreting this sentence, which is going to be more difficult because we require a special type of categorical semantics for universal quantification. Okay, so then you have this fact. Every accessible category is the category of models up to equivalence of a theory axiomatized by basic sequence. And so what we will see is that this allows us to define the accessible categories as the category of kappa points of a kappa topos. I will explain what are these notions, but essentially a kappa topos is a topos with some exactness property. It will end up being a kappa exact localization of a pre-shift category, but more than that. And kappa points is just a point, so a geometric morphism from set whose inverse image preserves all kappa small limits. Okay. And so I wanted to, so this is the fact that I mentioned before, this asymmetry between the indexing cardinality of disjunctions and conjunctions and the cardinality of the variables existentially quantified is there because that's the only way to be able to develop a formal deductive system for this logic of accessible categories for which the completeness theorem can be proven. So in fact, the idea of this all, the engine which is behind all this proof of Scheler's conjecture is a completeness theorem for this type of logic. And the only way to make it work is if we let the indexing cardinality of the disjunction be bigger than that of the conjunction and the cardinality of the existentially quantified variables. If you were to use the same indexing cardinality for both of them, so when the positive existential formula is in the logic L kappa kappa, so the same indexing cardinality, then I have recently developed a proof sketch that there is no possibility whatsoever to prove a completeness theorem for which the notion of proof is transfinitely recursively definable. So no definable notion of proof can be given in that case, and so it's really needed here for to allow the completeness to work. Okay. And as I said before, this sequence style will allow to have a smooth definition of the categorical semantics. So let's quickly overview what's behind this logic system. So remember that we have a certain type of formulas, and now we want to establish the concept of proof in that system. So when is a proof? Well, a proof is a tree whose nodes or leaves are axioms, and which is built using inference rules from several different sequences. I can infer another sequence, so that builds a further node. And the tree can be infinite in the sense that it's infinitely wide, but it needs to be, all the branches need to be of finite height. So there is always a finite number of steps from the final sequence that you end up proving to an axiom that you use in the proof. Okay, so let's quickly review these. We have what will be the axioms and the rules of inference for this system of kappa coherent logic. Of course, the identity axiom. Then we have substitution. So whenever we have a sequence, we can substitute the variable x by terms and change here the context. This is called the context, the set of variables that are here. All this is designed to have a nice categorical semantics. We will see later that this substitution is just interpreted as pullback in the appropriate categories. The cut rule, which is an inference rule, so you have two sequences like that, and it allows you to deduce this sequence here. So there you are building a tree with two sequences as leaves, and then this is the root. You can continue this tree by using several other rules of inference and axioms. So these are the axioms for equality, are quite standard. So they just say that you can replace in the formula tuples of variables by another tuple as long as you have an equality between them. The conjunction, this is standard as well. So you have here both an introduction and an elimination rule. So here you can eliminate the conjunction by putting one of the conjuncts here, and conversely, if you have a gamma many sequence of this form, this is what this means. So this is a set of gamma different sequence, which are the leaves of the tree. You can deduce this sequence introducing the conjunction here. Dually, you have the converse for this junction. You have an introduction rule for the junction and an elimination rule as well. And it's just the duals of the previous rule. But this is all standard in logic. Then here comes something interesting, because you have the existential rule, which is a bidirectional rule. So you can go from one sequence to the other indistinctly. And here the effect of the existential quantification is to reduce the number of variables in the context. This, as we will see, will be interpreted as a certain adjunction between the subobject lattices. So the existential quantification will be interpreted as a left adjoint to the pullback factor between subobject lattices. Okay, that's it. Then we have these technical rules, which are just distributivity, the small distributivity, and Frobenius axioms. And the key new rule of inference that we put in this type of logic to allow for the completeness theorem to hold, it's a quite complicated rule, so I will just hover over it, but I mean, you don't need to understand it entirely, just to take a look at it, and then the categorical semantics will be much easily graspable. Is the transfinite transitivity rule, which is some horror like this. You have plenty of sequence. Essentially, these formulas are indexed by nodes on a tree. And so this first set of sequence here will say that one node of the tree, the formula there, is covered by the nodes on the successors. Then you will have a set of sequence that talks about the what happens at limit levels, at limit levels of the tree. What are the formulas in the nodes at the limit levels? They will just be the conjunction of the formulas of the predecessors. And the conclusion of the rule is that the root of the tree is covered by all the nodes, the utmost nodes, so the leaves, essentially. If you think of it in this way, what it's saying is that imagine for a moment that you have Grothendieck topologies. There is a transfinite property for the Grothendieck topology, which says that if you have a cover, and on the domain of each of the arrows in the cover, you have another cover, so another set of covering families, then you compose all those, and you get still a cover. This rule is saying precisely that for the transfinite case. So you have not just one cover of top of the domain of each arrow in a certain cover, but you have also covers in those, and so on and so on. And you can go transfinitely by taking limits. And this rule just says that the transfinite composition of covering families are covering. All right. So this logic, now let's go to the categorical semantics, which is the most interesting part. This logic cannot just be interpreted in structures in set, but actually in any sufficiently similar category. So any category which has set-like properties, if you will. So these are the kappa coherent categories. It's just a regular category, so it has stable images, epimonofactorizations, which has kappa small limit. It has unions of at most kappa many subobjects in the subobject lattices, and satisfies this transfinite transitivity property, which is that transfinite composites of jointly epic families of arrows is jointly epic. And so examples of this kind of category. So the first immediate example is set, of course. This transfinite transitivity in set just is a combination of distributivity and dependent choice, which we assume that they hold in set. But in fact, any pre-shift category is also kappa coherent for any kappa. Then, if you take up a pre-shift category and on the site you make a site out of the category C by putting a topology, a Grothendieck topology, which satisfies the transfinite transitivity property, so in which transfinite composition of covers of the topology are still covering, then you will get a shift topos, which is again a kappa coherent category. So as long as you start with a site with a category with kappa small limits, you put a topology with the transfinite transitivity property, and then the corresponding shift topos will be a kappa coherent category. And in fact, any example of a kappa coherent category can be built out of the syntactic category of any theory. So you choose the sequence in this kappa coherent logic we've seen. All right. So what about the semantics? So because we have so far the syntax, and then we will like to interpret theories in structures, not just in set, but in any kappa coherent category. So to talk about a structure in a kappa coherent category, you can define what are the sorts. The sorts are the types of the variables that you use in your theory. And so you will have one object defining the sort. In general, our theories are unisorted, so we have just one object representing the type of the variable. And then you have morphisms representing the function symbol. So it goes from a product of sorts to another sorts, and this is intended to mean the function symbol whose entries are of corresponding sorts AI, and the application of the function to those to variables of those in those entries gives a term of sort B. And then the relation symbols are represented by monomorphisms. This is a relation symbol with an arity of alpha, so it has alpha many entries. So it's just a subobject of the product of the AIs, which are the sorts of the corresponding variable. Okay, now terms are interpreted as arrows. So for example, here you have the interpretation of the function symbol, which is just an arrow. But also you can compose terms, and this is just the arrow composition in the category. So for example, if you have a term f of the y's I that goes from this product to C, and then here you have a list of terms G0, G1 on the variables xi, which are of type AI, and this is just the induced arrow into the product. So you have such a term for each bj, so that will be the codomain of each of these terms. You can compose, and it's just the arrow composition, and you will get the interpretation of the corresponding composed term. Now, formulas. Formulas are interpreted as the subobjects of the product of the sorts of the free variables in the formula. And this can be defined inductively on the complexity of the formula. So for atomic formulas, for example, as soon as you have the interpretation of a relation symbol here as a subobject of a product of sorts, if you want to interpret the formula, which is the relation symbols applied to certain terms, then first you put the arrow representing that term, and you form the pullback. So the pullback will be a subobject of the products of the pj, which are the types of the terms tj, and this subobject is then the interpretation of this atomic formula. Then the other type of atomic formula is an equality between terms. This is just the equalizer of the corresponding terms. So this S and T represent here multiple terms. This equality means an equality between multiple terms, and you just take the equalizer and you interpret that atomic formula as the subobject. Then, since in a kappa coherent category you have unions and you have, since you have kappa small limits, you have intersections of subobjects, you can, in a formula containing those connectives, interpret using the structure of the kappa coherent category. And finally, this is what I was telling you about. The existential quantification is interpreted as a left adjoint to the pullback functor. So if you have here a formula which is, the interpretation of this formula is a subobject of this product of sorts, in which B is the sort of the variable Y here, then the interpretation of the formula in which you existentially quantify that Y will be just the image factorization of this subobject composed with the projection to the first alpha coordinates. You factorize it as an epimonofactorization, and this will be the subobject interpreting the existential quantification. So, in fact, what this is saying is that to any subobject of this product of sorts, you assign another subobject of this other product of sorts, which happens to be the left adjoint to the pullback functor between subobjects of these two subobjects of this. And this is precisely capturing the bidirectional rule of inference that we had introduced before for the existential quantification. Okay. Now about syntactic categories. So this is all standard. We just the new stuff here is that we are interpreting a kappa coherent theory. So it has that extra rule, the transfinite transitivity. And essentially the syntactic categories, we saw the universal property in the last talk, but we can now give a purely syntactic construction, an inner way of building it. Objects are essentially kappa coherent formulas in context. So you choose a formula, you choose a set, a tuple of variables containing the free variables of phi, but could contain more variables. And then you are free to rename all free and bound variables as long as you are consistent with the renaming. So in phi, if you change an x for a y, you have to change that x for a y here. But that's the meaning of alpha equivalence. So those are the objects. And the morphisms between two objects are just also equivalence classes of formulas in the combined context, x and y, and which are provably functional. So such that the theory proves that this formula, which has free variables x, y, is the graph of a function between phi and psi. So those are is just saying that the formula theta, phi, and psi here satisfies certain sequence that witness that this is functional. Okay. There is a canonical structure in every syntactic category. You have x and the formula true, the top formula. So the top element of the subobject lattice is the interpretation of the sort corresponding to the variable x, a relation which should be a subobject of products of sorts, and functions, which should be arrows between products of sorts and p, should be interpreted as these formulas in these contexts. So essentially you have a canonical structure in every syntactic category. And now the theorem in this case is that the syntactic category of a kappa coherent theory is a kappa coherent category. So all the categorical properties of a kappa coherent category are satisfied in the syntactic category. Moreover, the canonical structure will be an initial model of the kappa coherent theory. And in fact, any model of the theory in any other kappa coherent category D are precisely the images of the initial model through kappa coherent functor. A kappa coherent functor is a functor that preserves the kappa coherent structure of the category. And well, if it preserves the kappa coherent structure, it will preserve the interpretation of each formula. So it takes a formula to its interpretation in the kappa coherent category D. So there's just a unique such functor taking the initial model to the model in D. So this is the factorial semantics that we have for the category. And the new part here is the satisfaction of the transfinite transitivity rule. So in this case, it will mean that the kappa coherent category transfinite composites of jointly epic families are jointly epic, and is completely straightforward, but tedious to prove because you need to essentially talk about how do you build kappa small limits in the syntactic category. So you need to play a bit with the theory. Okay, now we also mentioned last time the kappa classifying topos of the kappa coherent category. This will just be another syntactic incarnation, but instead of staying in the doctrine of kappa coherent categories and kappa coherent functors, we pass to the doctrine of kappa toposes and kappa geometric morphisms. So a kappa topos is a kappa coherent topos, so it satisfies this transfinite transitivity property. And a kappa geometric morphism is a geometric morphism that preserves, whose inverse image preserves kappa small limits. Remember that a geometric morphism has two parts. It's an adjoint pair between the direct image and the inverse image, and is the inverse image the one that preserves kappa small limits. So the theorem here is saying that the kappa classifying topos of T, whose universal property we saw last time, the universal property being that any model of T in any kappa coherent topos E corresponds to an essentially unique kappa geometric morphism. So one whose inverse image preserves kappa small limits, sending the model inside, the initial model inside the topos to the model in the topos E. And the theorem here is that there is an inner construction, a syntactic construction of the topos of sheaves, of the kappa classifying topos, is just taking sheaves on the syntactic category with a topology given by specifying that the covers of the Grothendieck topology are jointly epic families of arrows. Since we started with a kappa coherent category, that will satisfy the transfinite transitivity property, and so as we saw before, the topos of sheaves satisfies the transfinite transitivity property, so it's a kappa topos. And so,
sorry, listen, one question.
Yes.
E doesn't need to be kappa coherent, meaning that in classical topos theory, you just take models in any Grothendieck topos.
Right, but this property of the definition of kappa classifying topos takes place in the category of kappa toposes and kappa geometric morphisms.
Okay.
So the universal property for the kappa classifying topos is that you need this E to be a kappa coherent topos, and then you will have an essentially unique kappa geometric morphism corresponding to the model in that kappa coherent topos. So you shift to the kappa coherent doctrine here.
So E needs to be kappa coherent.
Yes, that's the definition of the kappa classifying topos. Otherwise, it would just otherwise it would just coincide with the classifying topos, and we saw that can't be the case because the kappa classifying topos is a different topos.
Okay.
All right. How are we with time? Okay. Maybe I should hurry a bit. So, and now we have come finally to the thing that I've been saying last time during last talk, and which has to do with the preservation of sequence. If a sequence, what does it mean first for a sequence to be valid in a kappa coherent categories or in a kappa coherent topos, in a kappa topos? That the interpretation of the corresponding positive existential formulas, one factors through the other. Both are sub-objects of the product of sorts, And saying that the sequence is valid is saying that the interpretation of one, which is a subobject, factors through the interpretation of the other, which is also a subobject. So in this way, you can see that if you have a kappa coherent functor, so in particular it preserves kappa small limits and in particular monomorphisms, if a sequence holds in A kappa coherent factor will preserve its validity. So it will hold in B because it sends monos to monos, and it sends the interpretation of formulas to interpretation of formulas in B. So you see that this is the reason why we have to choose sequence to be able to get to this level of generality. Without introducing universal quantification yet, we have sequence here. And just kappa coherent functors preserve the validity of sequence. Similarly, for the inverse image of kappa geometric morphisms, if you have a sequence which is valid in a topos, then the inverse image of a kappa geometric morphism preserves kappa small limits. So in particular, it preserves all the kappa coherent structure of the sequence of the formulas, of the positive existential formulas. So it will preserve the validity of the sequence as well. All right. And now the first completeness theorem I wanted to talk about, the Topos-theoretic one, is that this completeness theorem for kappa coherent logic, validity of a sequence in set implies the probability in the proof system of before, is the same as saying that the syntactic category admits a jointly conservative family of kappa coherent functors into set. And this, by the universal property of the kappa classifying topos, is the same as saying that the kappa classifying topos has enough kappa points, has a set of jointly conservative inverse image of kappa geometric morphisms into set. So this is the content of the infinitary delineate paper. Since last time we were under GCH, then we have for free this assumption for any regular kappa to the less than kappa equals kappa. And then in that case, the kappa classifying topos of a kappa coherent theory, which has at most kappa many axioms, has enough kappa points. This is the infinitary delineate theorem. This is what we've been using last time at several points.
And this is just from a geometric point of view that a kappa separable kappa topos has enough points.
Exactly, yes. A kappa separable topos is a topos in which the site has size kappa and the topology is generated by at most kappa many covers. And the restriction here on the amount of axioms of the theory implies the separability of the kappa topos, and so this is just the same as saying a kappa separable kappa topos has enough kappa points. So if we go back to the idea of axiomatizing the kappa saturated models that we saw last time, let me remind you how it was. We had first, because of the theorem of last time, the classifying topos of T kappa, the theory of models of cardinality at least kappa, was a pre-shift topos. That was the main theorem of last time. And what would be the Yoneda embedding in the syntactic construction of the kappa classifying topos could be identified with the evaluation functor here. Then, if we add sequence, kappa coherent sequence to the theory, saying that there are kappa, at least kappa plus distinct elements in each of the models, then we get a subtopos here, because adding sequence is the same as adding covers to the Grothendieck topology. And if we have more covers, we have a subtopos. So, and then what I proved last time is that the syntactic category of kappa saturated or kappa plus saturated models has the kappa plus classifying topos of that was precisely this thing here, which was the double negation subtopos of this preshift topos. And that I wanted to explain here. The double negation subtopos is built as the subtopos corresponding to the dense topology. A topology is dense if a covering family, arrows from AI to A, belongs to the topology when for every arrow from B to A, there exists an arrow from C to B such that this composition factors through one of the arrows in the cover. That defines the dense topology. So in particular, you see that this is a property of the subcategory of models of size kappa, op. So this op means that if we reverse the arrows, this is just the amalgamation property. So in particular, if you take in K kappa, if the AEC had the amalgamation property, K kappa will have the amalgamation property, and you can just take covers consisting of single morphisms, and that will be the dense topology. When the cover consists of a single morphism, that is called, so non-empty sieves are covering, that is called the atomic topology. So that is what is going on here, that the amalgamation property on the AEC implies that you can take just single morphisms here as covers for the dense topology. So this topos here, which I proved last time was the kappa plus classifying topos of the theory of kappa plus saturated objects, saturated models, is just the localization of this preshift category with respect to single morphisms. So you take a morphism from one representable to the other, and that is going to be taken in a universal way to an epimorphism in this localization. This is what I said. So this is what I said before in the previous talk. So that is the way that you find that this is the kappa plus classifying topos of the theory of kappa plus saturated models, because any kappa plus saturated models sends a single morphism here to an epi, so sends this to an epi, so it must factor through the universal way of making this single morphisms epi, which is this double negation subtopos. Okay, and now to the second theorem of completeness theorem, Topos-theoretic completeness theorem that I used in the last talk. This has to do with interpreting universal quantification. So we know that the inverse image of a kappa geometric morphism preserves the validity of a sequent. However, a sentence should be interpreted as a subobject of the terminal object of one, because you don't have free variables there. So it's just the empty product of sorts, which is the terminal object. And it might happen that the interpretation of the sentence is not preserved by the inverse image of a kappa geometric morphism. In fact, you preserve the sequent, but to preserve the interpretation of the sentence means that this functor should additionally preserve universal quantification. So not every kappa geometric morphism does preserve the sentence. However, we can characterize those who do, and that has to do with the categorical semantics for the universal quantification. First of all, there should be a syntactic bidirectional rule that tells us how to deal with universal quantification. It just says that if theta and phi entails psi in this context, then theta should entail that for all x, phi implies psi. And this should be if and only if. So what this is saying, this is the dual rule of the existential quantification rule. So this is just saying that instead of interpreting the universal quantification, in the same way we interpret the existential quantification as a left adjoint, we are now going to interpret the universal quantification as a right adjoint. So if we have a sub-object here, pullback along phi gives us theta and phi. And these factors through this sub-object, psi and phi, by hypothesis, because this is the first sequence telling us here. And what the bidirectional rule is telling us is that that is the same as having theta factoring through this other sub-object, which is the interpretation of this second sequence here. So you see, there is an adjunction between the sub-objects of this and the sub-objects of this. The pullback is the left adjoint to the interpretation of the universal quantification. So we can say that the universal quantification is interpreted as a right adjoint between pullback factors, and so a sentence is preserved by a factor if the factor possesses right adjoints to pullback. So because of this connection with the logic here, the right adjoint along f of a subobject A is denoted as for all fa. That f preserves it means that if I compute f of that, I get the same as taking the right adjoint along f of the subobject f of A.
Is
so
this a kind of Beck-Chevalier condition?
It's related to that in that we will have this property by taking the Beck-Chevalier condition and looking at the adjoints to the existential and to the pullback factor. So yes, it's in fact related to that.
Okay.
And this is the last piece of completeness that I used in the previous talk, saying that this evaluation factor preserved this sentence. Saying that is actually what this infinitary version of Joyal's completeness theorem is saying, is that this evaluation factor preserves right adjoint to pullbacks. As soon as we prove that, then we prove that it preserves this sentence. And I remind you of the proof. The proof was very simple, was just noticing that this pre-shift topos by the main theorem of last time is just the lambda plus classifying topos of t kappa plus. And so the evaluation factor here is just the inverse image of the geometric morphism G star, which is induced by the canonical morphism between the syntactic categories of the theories with the kappa plus distinct elements and the theories in the logic L lambda plus. So this, because of the construction of the syntactic category, you can add the rule for universal quantification to the logic, and you get what is called a Hayting category, which interprets that formula as the right adjoint to pullbacks, as we saw. And because of the construction, it doesn't matter if you're in the logic L kappa plus or L lambda plus. The interpretation of that right adjoint will be the same in both, will be the same formula. So this preserves universal quantification. And by the construction of the kappa plus classifying topos that we saw today, is just constructed as Yoneda embedding into the topos of sheaves with a kappa topology. Boots and Johnston in 1998, they proved that Yoneda embedding preserves right adjoint to pullbacks. So the commutativity up to ISO of this diagram means that this preserves right adjoint to pullbacks, and so this preserves the sentence. So the last thing we used last time was the Kripke-Joyal semantics. So let me tell you a bit how that works. First of all, in any shift topos, the right adjoint to pullback can be interpreted is a subsheaf. So it's a functor, is in particular a presheaf, and is defined by this formula. So the presheaf on an object C contains an element Y if and only if this happens. This is the definition of the right adjoint to pullback in a shift topos. In particular, if it's a presheaf like this one, there is an easy rule for computing using the Kripke-Joyal semantics. This semantics is available in any topos whatsoever, but it's most simple in case of presheaf toposes. What it says is that one defines what it means for an object of the category K to force phi of alpha. It just means that the arrow from M to the topmost object, interpretation of the object in the presheaf topos, factors through the subobject corresponding to the interpretation of the formula. And you see here that since this was the evaluation functor here, then the interpretation of these formulas are just the evaluations in true and evaluation in phi. And so an arrow from M to the evaluation is just an arrow from, is the same as by Yoneda as an element of evaluation in M. And the evaluation of phi in M is the extension of phi in M. So what this commutative diagram is telling you is that for kappa coherent formulas, this forcing notion is equivalent to validity in the model. It's equivalent to the model satisfying the formula when evaluated at the element alpha of the model. Here we are by Yoneda identifying elements of the underlying set of the models with arrows from M to this interpretation. Okay, and but the Kripke-Joyal semantics works for any phi, even if it's not kappa coherent. So, and in fact, using just the definition that I gave you of the forcing notion, you can prove that for formulas that contain universal quantification or the implication or the negation, the following easy computation rules apply. M forces an implication if and only if for every arrow in K from M to N forces phi of F alpha implies N forces psi. The negation is just the implication phi implies bottom. So this second item here is a particular case of the first. Since no model forces bottom, because it's the same as validating bottom, which is not the case for any model, then this will happen if and only if for every arrow from M to N doesn't force phi of F of alpha. And finally, the clause for universal quantification says that enforces this formula if and only if for every f from m to n and alpha in the underlying set of n enforces phi of alpha, phi of f of alpha. So if you remember what we talked last time, we had a diagram like this. This was the kappa plus classifying topos of the theory of models of size at most kappa plus. We had the double negation subtopos. We had here an isomorphism between these two Scott toposes. And we were assuming that the AC was categorical in lambda. So we wanted to prove that that implies categoricity in here. And the strategy was proving that these two toposes coincide, because that would mean that every model is in fact saturated. This is the kappa plus classifying topos of kappa plus saturated models. So if every model is saturated, we have categoricity. So what I said is that the way to prove that this was an an equivalence, was proving that every sentence, every basic sentence satisfied in here is also satisfied in here. Now, the basic sequence corresponding to the sentence is preserved by this morphism, so it's valid in here, and so in particular it's valid in the unique model of cardinality lambda, because that is a lambda point of this topos. So in fact, the model of the unique model of cardinality lambda satisfies this sequence for all x phi implied psi. That means that it cannot possibly force the negation, because forcing the negation according to the previous set of clauses for Kripke-Joyal semantics would mean that for every morphism from m lambda to another model of cardinality lambda, this other model does not force the sequent. But since we are assuming categoricity in lambda, this other model will be isomorphic to m lambda, so it will have to force this sequence. So m lambda does not force this. And then we have the evaluation factor in the second completeness theorem, which told us that if the negation of this sentence is not satisfied here in the preshift topos, then is not satisfied here either, because this is conservative and this topos we saw it was two valued. So there are two possibilities for the interpretation of the sentence. Others is 0 or is 1. If it's 1 here, because this evaluation factor preserves the sentence, because it preserves right adjoint to pullback factors, that is the content of this infinitary Joyal, then this would have to be true here. But it can't possibly be true, because by the Kripke-Joyal semantics clause for universal quantification, this preshift topos does not prove this sequence, because there is a model which doesn't force it. A sentence is valid, universally valid here, if all the models force it, according to the definition of forcing. So this sentence cannot be 0 in this kappa plus classifying topos. And since this is two valued, it can only be the case that it is 1. And being 1, the interpretation of the sentence being 1 means that the sequence, the corresponding sequence, is valid here. So that is the way of transferring validity in here to validity in here. And that was the way of proving this downward transfer of categoricity. Okay, but then it's time, so I should stop here. Thank you.
So thank you, Christian. As always, we have silent applause. So Christian cannot hear you, unfortunately, but I hope everyone has liked the talk. And so now, if you want to make a comment or you want to speak, to ask a question, please unmute yourself and say whatever you think.
Yeah, I have a question.
Yes.
Has this theory of coherent logic and the relationship to their classifying toposes been developed in the proof relevant context? Do you know that?
In the proof relevant context?
Yeah.
What do you mean?
So, I mean the calculus you presented in the beginning. You have the sequence.
Yes.
I mean you could do the same thing in a proof relevant way, which is basically type theoretically. So you have terms that prove your formulas, and then you have to manipulate those terms or those proofs in order to give a proof of.
Right. No, it has not been done type theoretically. So this kappa coherent logic was introduced in my paper on the infinitary linea theorem, and there I prefer to use the sequence style approach, so that I will be able to build a syntactic category out of the formulas, the positive existential formulas.
And in the finite case, do you know either?
No, in the finite case, that is known. That is just coherent logic.
Yeah, even proof
or geometric logic, because we are taking in account the asymmetry between the cardinality of the disjunction and the conjunction. So it's just geometric logic.
Has the finitary case been done in a type theoretically or in a proof relevant way?
I'm not aware of it.
Okay.
So if anybody has another question, just keep unmuting yourself and keep asking questions. I will be silent.
So I would like to thank you for this. This is exactly what I was hoping for. A sort of non-mathematical question. There are a lot of model theorists who'd like to understand this proof. Would it be okay if I share the website and everything so they can?
Yes, of course. Yes. Yeah. These slides will be uploaded, and there's also the video if they need, and they can contact me, of course, in case of questions.
Excellent. Thanks.
So, okay, if there are no more questions, we thank again the speaker. Thank you again, Christian. And before leaving you, maybe I will just say that next week we have Soichiro Fuji talking about a unified framework for notions of algebraic theories. And it has been a pleasure to host all of you. And I think we are done for today.
Okay, thank you.
Yeah.
Thank you.
Bye-bye.
Goodbye.